geometry of the unstructured grid. And this is taken from CPAS tutorial. These cells is called Voronoi tessellation. And there are two more adjectives in front of it. Centroidal, that means you can change the something like called density of the cells. For higher resolution, you have higher density, and for lower resolution, or lower density. And then the cell center is located somewhere in the cell according to the weighted density, according to the way that it is central of the cell, but it is weighted by the density. So, okay, so you have this name, and then for CPAS, it is a model for the atmosphere. So it is in a spherical geometry. So very often in CPAS documentation, you see spherical. Then coming up is CVT. That means this Voronoi tessellation. So one way you can understand Voronoi tessellation is that suppose you are in some historical period that on a piece of land, there are many kings, and each king has a castle, like the way in Japan or in England. In Japan, it is called Daimeng. In England, you may heard of a lot of stories about kings and princesses. So they live in a castle. And then actually, as they are king or as they are Daimeng in Japan, they are requesting farmers that live near to their castle to pay tax to them. But you know, over the land, there are a lot of kings and there are lots of Daimeng in Japan. So if you are a farmer, usually you pay tax to the king nearest to you, and then you will be protected by the king. So using this logic, you partition the space like this. Everywhere in a cell, if you pick one point, and then you calculate whether this king is nearer to me, or this king is nearer to me, or this king, your result is this king is nearer to me. So this is a boundary between two such kingdoms. So this will become a Voronoi cell. So simple, we don't go to mathematical geometry right now. And then we look into data structure. Last time, we can open a generated grid netcdf file and put it to a data set. And you remember in the data set, there are data variables. So the geometry of this unstructured grid is described by cell, which usually means the cell center. And then vertex means these vertices. And then edge, usually we use the point at the center of the edge to represent the edge. So this is like what my mouse is at. And then in the grid.nc file, there are data variables that contain the data about each location's latitude and longitude. Say, for cell, you have lat cell and long cell. And how about this dimension? This dimension is n cells. N cells is a number of cells. So in this grid.nc, you have a dimension which has more than 100,000 cells. So this dimension is like this. And then you have two arrays. One array is lat cell of this length. Each element is the latitude of the cell center. And then for longitude, you have another variable, long cell, and then using the corresponding index, it is the longitude of the cell center. Okay, the data description is like this. And for edge, it is described in the same way. You have lat edge and long edge. So it is this location, the center of the edge, the lat long of them. And then for vertex, you also have the same thing. Okay, next. Neighborhood. As I introduced earlier, the line connecting one cell center to the other cell center can be drawn, and that will become a triangulation. And there is another property that this triangulation are actually called Delaunay triangulation. And so you connect all these neighborhood lines and you have a triangular mesh. That mesh can be called a dual mesh. So the Voronoi mesh can be called the primal mesh, and this connected triangular mesh is a dual mesh. This is quite complicated if you compare to rectangular mesh, because everything will just become plain two-dimensional array, and you do not need index to describe them. But in MPAS, you have to use a lot of index. Here is it. So each cell is given an index, like this is the third cell, this is the fourth cell, and something like that. And then the information are put into one-dimensional array. And then neighborhood information is put into something like what on what. Say you check cells on cell. Like this example, the seventh cell is at the center. It has 6 cells on itself. So it is called cells on cell. And then the index of its label will be put into these data variables. So for each cell, it have to be put to this variable. So one dimension of this variable is n cells. And then another dimension is maximum edges. So how many neighbors can one have? For CPAS mesh, because we are using a special algorithm I mentioned before, which is an OLAM-based construction, it has a property that only heptagons are used, no more polygons with more edges. So the generated file has max edges, dimension being 7. So for variables that describe neighborhood, it will be 2-dimensional array. The second dimension will be this max edges, and then they will put the first neighbor is number 8. So number 8 is cell 7's neighbor, and then the second neighbor is number 11. Number 11, the second neighbor, so on and so forth. So you will see these variables in this screen capture, not there in your lab. You will see it yourself. And then I have to introduce some important field to you. One is the DCH, which is actually this one, DC, the distance between 2 cell centers. It is actually something related to grid spacing. As you know, each cell usually have 6 labor, some have 5 or some have 7, and then the length from the cell center to each labor can be different. So there are say the number of neighbors is 6, then you have 6 DCH associated with each cell. And then when we mention grid spacing, usually we are saying the average DCH associated with a cell. And then the areas are actually used in the simulation, but I don't go over them here. And dimensions I have introduced. And then for the vertical grid, here are the details. As usual, scalars like temperature are defined at the center of the vertical span. And then the vertical wind are defined at the face of these vertical cells.